Okay, so here is number 22 in section 8.3. This is similar to number 21, which is a homework question. And it's a function that's written as a recurrence relation. And we're going to first just find a value of the function, and then we're going to give it, give a big O estimate for the function, okay? And we're going to rely on a theorem. Okay, let me pull this up. So this is the main theorem of this section, where it gives a big O estimate of a function of the form f of n equals af of n over b plus c n to the d. Okay, and obviously the one that we have up above here, this function here, is not written in this form. But what we can do is we can do a kind of change of variables and get a new function in this form that we can get the big O estimate from. Okay, so that's what we're going to do. But first, let's just find f of 16. So f of 16, this is 2, f of square root of 16 is 4, plus log 16, and then f of 4 is, f of 4 will be 2 f of 2 plus log 4 and then plus log 16. And then we have the initial condition f of 2 equals 1 up here. So this equals 2 times 2 times 1 plus log 4 plus log 16. And then we can maybe do some simplification. So let's see. We get 4 plus 2 log 4 plus log 16. This is going to be 4 plus log 16 plus log 16. So it's going to be 2 log 16. And so this becomes 4 plus log of 256. Okay. And this is going to be just over 2, about 2.5, right? Just about. So this will be about 6.5. But of course, you can use a calculator to get the exact answer. Okay, so next, let's move on to finding the big O estimate. So let me clear this out here. And yeah, let's find the big O estimate of this function. Okay, so we have a square root, which is a kind of unusual power. It's a fractional power. And so one trick with working with fractional powers, if we want to get equivalent functions that are kind of easier to write or easier to manage, we can use logarithms, because powers and logarithms become constants, okay? In other words, if we let m be log n, then if we look at like log of square root of n, this is just going to be, well, let me go forwards first. So this is going to be log n to the 1/2. We can pull the 1/2 in front. So this ends up being a half of n, okay? So what we're going to do is we're going to define a new function, okay? Let's call this g of m. Define this to be f of n, okay? Where m is log n, okay? So look what happens when we do this. F of n is 2f square root of n plus log n. That's the definition of f of n. And this is equal to 2g of log square root of n, okay, by definition. F of square root of n, f of any number is g of a logarithm of that number, okay? Okay. So this is our change of variables. And then what we just showed above was that log square root of n is just the same thing as 1/2 of m. And then log n is just equal to m. Okay, so what we have is this new function, or not really a new function, it's actually the same function. That's actually the key point. It's the same function written in a different form, okay? So we took f of n and rewrote it as g of m, and we got g of m equals 2, g of m over 2 plus m. And now we can, let's go pull back that theorem. Pull it up here. Okay, so now we have something in this form where A is 2, B is 2, C equals 1, and D equals 1. Okay, that's what we get. We're just replacing the F's with a G, replacing the N's with an M. We get these constants, which means, let's see, A is, so B to the D is just 2. So in this case, A equals B to the D, right? 2 equals 2 to the 1. And so Fn is, so actually, G of m is O, m to the D is m to the 1, and then log m, which means that Fn is O, m is log n, so log n times log of log n. Okay, so that is our final answer. It's kind of written in a little bit of a weird, or the answer looks a little bit weird, but that's exactly what we get from the theorem. So this is kind of our measure of complexity for this recurrence relation.